Swayam Prabha. Digital India. Educated India.
I think we have an audience who's like coming from BTech second year to BTech second year to even faculty members, right. So, it's a the range is wide. So, we will see how we cope up. Now, can I know if anyone has any introduction to computational geometry in your algorithms course or as an elective? Can you just raise your hands? 1, 2, 3, 4, 5. Okay. So, what do you know of computational geometry? Huh? No, I asked to raise hands if you know something of computational geometry. Okay. So, it's almost nil, right? Fine. So, computational geometry is kind of 40 years old subject, I would say. What it deals with is like your graph algorithms. So, it deals with graphs, right. Computational geometry deals with geometric objects. What they are? So, we deal with points, some properties over points, lines, line segments, circles, and so on. So, geometric objects with you can think of a geometric object, say a circle, as an algebraic curve, okay, x square plus y square equals to 1 or r square. So, you can also deal with algebraic curves. Polynomial is kind of an algebraic curve, but to start with we would focus our attention on geometric objects that can be represented in a very succinct and a precise way. So, point, you need a coordinate, right. If you are in d-dimensional space, you need d coordinates to specify a point. Say let us talk 2D to start with. So, you need 2 coordinates. For a line, you need y equals to mx plus c. So, your m and c defines a line. If you have a line segment, you need its starting and ending point. If you have a circle, you possibly need its center, coordinates of its center and its radius, right. So, this is what I mean by a succinct or a precise small representation of a geometric object. So, the objects would come to you in this fashion and we have to do something, compute some properties over this geometric objects. Now, some of you who must have written programs in graphs, graph is about a relation, right. So, you have a set of vertices and you have an edge set which is a subset of V cross V. So, it encodes a relation. So, in geometry we operate mostly on sets. So, sets of points, sets of lines, sets of line segments, sets of circles, sets of geometric objects. Now, to write programs in geometry is not as easy as probably writing programs in graphs is. I will give you a small argument why it is not going to be so easy. Now, think of a y equals to x line through the origin, right. Now, look at the 1 1 coordinate. So, the equation of this line is y minus x equals to 0, and if you replace the coordinates of the points on a line, you should get 0, right. Okay. Now, think of say maybe analytically this should also do the same as 1 1, right, but try writing a program for it. You would fail because our world is discrete and it supports finite precisions, right. So, essentially for most of the talk we would assume that when I talk of points or lines, I will deal only with rational coordinates, finite precision rational coordinates, right. So, that is what we would look at. And finite precision, and we would sort of look at rational coordinates. So, I started by giving you a very simple example. So, as you go along, there would be more and more problems. Now, to deal with programming in computational geometry, there are now dedicated softwares. One is this LIDA, it is known as the Library of Efficient Data Structures and Algorithms. So, this is not a fully dedicated geometry software. It has graphs, it has number theory, it has quite a lot of algorithmic libraries. It is essentially a C++ library which you can its student it has now, it comes with a cost, but its student version is cheap. If I remember correctly, it was around 49 euros a few years back. So, you can possibly even think of buying it. The other one is a free software and it is known as CGAL. It is Computational Geometry Algorithms Library. It is free. So, this is one which you can get your hands dirty with by trying to write programs in geometry. Apart from that, there are other dedicated geometry softwares like Core Library and some others, but for you it is like LIDA and CGAL is enough. So, CGAL comes for free, you can download and start writing programs in it. Okay. Now, because of this problems, to develop theory in computational geometry, we will make certain assumptions. So, the assumptions which would be just not an assumption in this talk, but would sort of continue over the entire duration of the workshop. It is like we would assume no 3 or more points are collinear So, we will assume that no 3 or more points lie on a line or no 4 or more points on a circle, right. That would make our analysis and life a little easy. So, let us start by looking at a very simple problem which you must have encountered in your school days, right. So, you know how to compute the area of a triangle, right, area of a circle, fine. Now, let us look at so this is say a convex polygon on n vertices. And the vertices are given say in a clockwise order. So, I will write CW for clockwise and if I want to write counterclockwise, I will write it as CCW. Okay. So, this convex polygon is given to you as a circular order of its vertices, fine. So, this is possibly your P 1 clockwise, okay. P 2, P 3, P 4, P 5, P 6, P 7, it is a P 8. So, it is given to you in this order, and your goal is, so this is your input, P is the input, and our goal is compute the area of P. What do you do? Divide it into triangles. Good idea. Now, how do I do? How do I divide it into triangles? There can be many ways. One is like take the centroid, add up all coordinates. It is a convex body, right? What is the property of? So, let us just wait here a moment, and possibly we will need this later on. Let us define what is a convex body. A convex body, a geometric convex body is one in which if you take any 2 points inside the convex body and join it using a line segment, then this line segment should be completely contained inside the convex body. So, say for example, this is not a convex body, because that part of the line segment lies outside, though there are points for which line segment lies inside, but again just the existence of one pair of points such that the line segment lies outside suffices, fine. So, you know what is a convex body, that you take any 2 points inside, you join the line segment completely lies inside, fine. So, this is what a convex body is. Now, your idea was, just get hold of one point and draw all of this triangles, sum of the area, right. So, how many triangles would you have drawn here? N, right, as many as vertices. Okay. We can possibly do a little bit better by doing it this way. Instead of starting from a point inside, what I do is I draw these things, right. So, how many triangles do I draw here? N minus. So, there is no diagonal going to a 2 of its neighbors, right. So, you can draw n minus 2 such triangles, fine. So, n minus 2 triangles, and these line segments which are within the polygon and obtained by joining the vertices of the polygon are known as diagonals. Okay. So, essentially we can get n minus 2 triangles by drawing n minus 3 non-crossing diagonals, because none of the diagonals cross inside the polygon, right. Now, this is a property that is true of any polygon. So, I showed you for a convex polygon, but it is true for any polygon, any simple polygon. We will see a short proof of it, or I will try to convince you why it is even true for any polygon, and Orithro will do this more formally later on when he talks of
Only it is for convex polygon.
no, it is for any polygon.
Even the polygon if it is not convex, it also.
I will show you why. So, let us now first look at a simple polygon. So, again I have a polygon with make it as complicated as you like, but the only thing is there is no hole inside and edges of the polygon cross only at the vertices, right. This is what a simple polygon is. Now, what you first do is look at the left extreme point of this simple polygon, right. Okay. Again, let us make an assumption that no two points have the same x and y coordinates. If there are ways in computational geometry in which you can handle it. So, look at the leftmost extreme point, fine. Okay. So, how does it look like? So, this is the leftmost extreme, and the rest of the polygon is this way. So, I look at the leftmost extreme point, let it be some v. So, it has two neighbors, let me call it as p and q. What I first try to do is I join it. Now, it can very well happen that it does not cut any of the edges of the simple polygon. If it has not cut, then I have got one diagonal, right, and I have divided the polygon into two halves. Look here. So, say for example, I mean if I get a diagonal like this, then it divides the polygon into two halves, fine. Okay. So, what I do is I join this line segment. If it is free of anything, I have got a diagonal, I have divided the problem into two halves, I can recurse. Else what might happen, whatever your simple polygon is, it can get inside, right. The part that has gone inside this triangle VPQ, for that I look at the leftmost extreme. So, this is the leftmost extreme. Now, if I join V with this leftmost extreme point, there can be no one obstructing me, right, because it is the leftmost extreme point inside this triangle, right. Again I divide my triangle into two parts, I can apply induction, I can recurse, right. So, you can think of this exercise. So, your exercise is show, possibly using induction, that any simple polygon of n vertices can be divided into n minus 2 triangles by drawing n minus 3 non-crossing diagonals. This result also has another significance, that is, if I look at a simple polygon and sum the internal angles. What is that sum? Look at a simple polygon, right. So, look at a simple polygon. And sum all the internal angles. N minus 2 into pi. The reason is because of this one, fine. This is what your brief introduction to geometry is. So, that point is like, so the computation of a simple polygon takes some time, right. It just does not come for free. Like if you have followed this induction, this is kind of can give me a divide and conquer, right. But what can happen is one part of the polygon can be very small and the other part can be big, and like in your quick sort you can end up having kind of an order n square algorithm to compute this area, but you can be intelligent and bring it down to order n. There are ways by which you can bring down this area computation to order n, right. So far everyone with me, right. So, you have got your first flavor of computational geometry. Now, let us look at a little bit serious problem. So, the problem is known as closest pair. In this your input is again a set of n points P in the two dimensional plane with the usual assumptions, and my goal is or to put it the other way, minimum distance among all pairs of points. Right. Given n points, tell me the distance between the closest pair of points. So, the problem is clear. Fine. So, what is the most trivial algorithm to solve this? Sort what? How do I sort n points? So, I sort the points on their x axis first, right. See, think of this. You
Suppose n points are there, we can n square solution will be computing GCD of every point.
GCD.
Yeah, that would give me how many points lie between those 2 points.
Why are you making the life complicated? Yes, that is the most trivial thing, right. Look at all pairs of points. N points, there are this many pairs, and which you know from your discrete maths is this, right. Look at all pairs, keep computing the distances, whichever is the minimum you report it, done. So, n square is trivial. What we want is to bring this down. So, beyond n square, what is your first guess? Something which is less than sub quadratic. What is the function you know? N log n, right. Okay. That is what we should aim at. And if you are aiming at n log n, and say by a divide and conquer algorithm, then also you know what can be your guiding recurrence, right. So, some idea which I would use from your study of algorithms. So, some things which I would assume that you know is like I would aim for something like this, right. So, our paradigm would be divide and conquer, and in divide and conquer, if I know that if I can get a recurrence like this, a recurrence like that, then I can solve T n into n log n, fine. So, what does this tell me? This tells me that divide the point set into two almost equal halves, right. So, how do I do it? I have to divide the point set into almost two equal halves. Give me a nice way of doing it.
So what guarantee is that they are uniformly distributed so that
I have not assumed anything on the distribution. They can be in any way they like.
Take 2 points which are at farthest distance and then
How do I compute that?
3 times. It's like the first point is that, otherwise it's this.
No, but how do I, no, the points, I showed you the input, right, one at a time. I showed you the input, right. The points are coming in any fashion, right. So, how do I know which one is the farthest pair? To solve the closest pair, you are taking me into solving another problem farthest pair, forget it. Next, yeah,
divide the set of points into equal halves.
yes. So, I have to divide the point set into almost equal halves such that their cardinalities are almost the same, right, save except 1, 2, 1.
It may happen at some point, the point at some position of the plane, the points are clustered and some where the points are sparse.
Okay, fine.
So then how can I make it equal? Become from those things and uniform.
This is what your point set is, right. Agreed. Still, can I not do it? Sort, okay.
Sort on the basis of x axis, and if 2 points are having on the same axis, we could sort them on the basis of y axis,
Uh-huh.
and then we could compute the, like we know the total number of points, so we could take
Now, see, I mean, you can do it, but there is a small catch into it. This divide and conquer recurrence asks you to divide. So, what does this, what is the story behind this divide and conquer recurrence? That I am going to divide it into two equal halves, and the rest work that I do, even for dividing these points and conquering or whatever, has to be order n, right. So, if you bring in sorting inside the recurrence, you are in for some trouble, right. We cannot get n log n. Okay. So, all of you have studied median finding algorithm, right. So, in linear time you can find the median, right. So, this is the knowledge I take from your algorithm study. So, that is we can find median in order n, right. So, what I do is I just look at the x coordinates of the point set, find the median. So, sir, where it will be, say somewhere here, right, and I draw a vertical line. The point sets are 2 into 2 equal halves, agreed. So, points on the left will have their coordinate values, x coordinate values less than equals to. So, let us call this to be some x med, this coordinate. So, point sets to the left, points to the left forms this set L, points to the right forms this set R. So, I have done this division using an order n time median finding, and then I looked at each point, figured out its x coordinate, and I divided. So, in linear time I have done this division. So, what is the situation we are in? We are in this situation where I have this is my left set and this is my right set, right, and I know assume n to be even. So, I know that the cardinality of L is n by 2 and the cardinality of R is also n by 2. So, now recursion, right. So, I can solve for the closest pair in the left half, solve for the closest pair in the right half, and say I get this distance to be some delta L, this distance to be some delta R. Now, I have to merge. Now, when I go to merge, see a point here and a point there are possibly not going to influence my closest pair, right. So, see if my closest pair comes from the left half or from the right half, I am in good territory, right. Now, what is the zone in which if the closest pair lies, I have to be very cautious when I conquer? That should be around this median line, right. Okay. So, that should be a region like this. So, if points are within this zone, I have to be cautious. I have to check on both with points on this side and on that side, fine. Okay. Now, let us define a quantity like this. It is the minimum of these two quantities, okay. And my claim is that I look only at this zone of 2 delta around the x made line. So, this was my median line. So, my claim is it suffices to look for closest pair contribution from the left and from the right. So, if there is a pair, right, whose one end is on the left side, the other is on the right side, it suffices only to look at this border zone, right. Agreed? So, if there is a point, say for example, here and a point here, they are not going to disturb my closest pair. Now, it might so happen all the points lie there, right, or even a constant fraction of n points lie there. So, how do we get rid of this problem? How do we tackle this problem? Now, for this, now just forget about this problem, this closest pair problem. We will come back to this very shortly. Let us look at a puzzle like this. So, the puzzle is as follows. So, you have a 2 delta cross 2 delta, so you have a 2 delta cross 2 delta square, and you have to place points inside this square. So, let this q be the square of 2 delta cross 2 delta. Our goal is place points inside q such that I give you now some conditions for this puzzle. Any point on the left side, so by left side I mean this line and to the left. So, this is the left side, close the intervals on this line and within this q. and this is kind of an open thing on this side, right. So, you have to place points inside this 2 delta cross 2 delta square such that for placement of any 2 points on the left, their distance should be greater than equal to delta, right. So, you have to place points such that, so you can place points like this, I have no distance restriction across the left and right region, but inside the left region all your points have to be placed such that the distance is at least as large as delta. So, in the left side you cannot place points very close, they have to be at least delta apart, right. Similarly, on the right side, right. So, you can place points as you like. I place no restrictions on across regions, but if you are placing points on the left, then you have to ensure that the distance between them is at least delta. Points on the right, the distance should be at least delta, but I do not give you any restriction when they are across. So, you understand the condition of the puzzle, right. So, such that you place maximum number of points as per the rule stated. Now, the question is, how many points can you place? 6. Only 6? Can someone not come up with a little bit better solution? So, you mean 6 on in total or 6 only on one side? 6 in total, okay. Can we not do it this way? So, a point here, 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 right, 5 points on this side, similarly 5 points on that side, right. So, I place a point here, place a point here, greater than equal to, I said, okay. What? Oh, acha, acha. Let us go for red. So, you can place a point here, here, right. You can place a point here possibly, right, maybe then here, here, right. Right, that is also one. So, then you can place kind of 9 points at all the corners, right. So, place one here, 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 forget about this one. But the question is, can this number be arbitrarily big? My argument would be like you cannot place more than 12 points, because you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right, 12 such edges. So, convince yourself later on. You can place only. So, what does big O of 1 mean? It is a constant, right. So, not more than that. So, you can possibly argue a little bit to make it 11, but 12 is a good number. So, think of it this way, that you can you have to place circles of radius delta to cover this 2 delta cross 2 delta square, and you understand there cannot be too many such. So, that is your argument, fine. Now, what does this puzzle, I mean let us look at the effect this puzzle has on our problem, right. So, this puzzle will have a bearing on our problem. Let us go back. So, let us look at the topmost point. Okay. And let us look at this 2 delta cross 2 delta square, which is hanging from this topmost point, right. By our previous puzzle, how many points can there be in this zone? At most a constant many, right. So, I compute all such pairs, distance among all such pairs 12 C2, again a constant, fine. So, the point is, for each anchoring of this 2 delta cross 2 delta box, I am computing only a constant many distances, right. I first do this, then what I do is I look at the next point, again I hang a 2 delta cross 2 delta box. Okay. Again I know that there will be only constant many points. Now, how do I retrieve, say starting from this point, starting from this point, how do I retrieve the next 12 points? So, for that what I do is, before I start my algorithm, I do a pre-sorting of these points based on their y coordinates, right. I do a pre-sorting based on their y coordinates. I have computed shortest pair of this, closest pair of this, closest pair of this. I have computed this delta. I know this region, and what I now do is I look at all points and pick up points which are only in this zone, but from that list which is pre-sorted on their y coordinates. So, that means I have the points ready with me in this order, which are in this zone. Agreed? Any doubts on this? So, that the idea is to have a pre-sorting, so that this n log n does not get into this recurrence in any way, because if this n log n gets into the recurrence, I cannot have n log n, it will get into something like more than n log n. So, the idea is do a pre-sorting on the y coordinates, keep the points ready with you, then get the median x coordinate, divide the point set into 2 halves, compute recursively the shortest pair on this, shortest pair on this, then you know this delta value. Now, go back to that list, pick up the points in this zone, that you can do in linear time, fine. And when you get this list, they are sorted according to their y coordinates. Now, get your first point, work on that list, pick the first 12 points, right. They can only lie within this, right. So, always look at the first next 12 points and compute the closest pair, right. So, there can be order n many points here, not more than that, right. For each one you have done 12 C2 many computations, constant, right. So, in all you need order n time to figure out the closest pair in this zone. If it falls below delta, you have got a new closest pair, else delta remains.
Square portion which we are taking between those delta lines, the delta region, two delta regions. So that square portion will be the distance from the lowest point to the highest point divided by the delta. That means square solve we need to take, or we need to take the
A square is defined by 1 point. So, you take the, so the points are sorted on the y coordinates, right, because what I did was I picked up the points in this zone from the sorted list of the y coordinates, right. I went around, so I have the sorted list of the points on the y coordinates, I marched on this list and just figured out that if it is lying within this x ranges, right. So, how is this point set now to me? It comes starting from this point to bottom, right. Now, what I do? I look at the first point and I look at its next 12 points on this list.
That's what I am saying. By going for the next 12 points, we need to just scan the number
No, 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 just the next 12 points. Just the next 12 points. And I am sure that the next 12 points are either in this zone or can even be, beyond it, right. So, I might over compute a little bit, but who cares? I am still doing order 1, right. So, what I do is I anchor this box at each of the points, right. So, how many such placements are there? N. Each point I anchor it once, right. And next what I do? I don't try to figure out how many points are within this box. I don't do that. Rather, I do it brute force. I look at the next 12 points, because I know that there can be at most 12 points in here, right. There can be less. I am over counting, right. Done? See, you can do to bring down the constant a little bit, but again, you cannot avoid n log n. That is the point. But then that should have been taken. See, when I computed the closest pair on this part and this part, no point was missed, right. So, I took this delta from this and this. So, this delta is a function of the closest pair here and the closest pair there.
So, but it may be possible that in delta L the minimum distance is suppose 1, and the 2 points in that delta region, one region in y axis are like 0.5 apart. They are just
0.5. No, no. So, you mean to say that there is a point here and a point on the right which are 0.5 apart, right. So, I can pick that up, right. What is the problem? Because I am, see, if they are 0.5 apart, if there is a 0.5 apart from this point on this side, this should come within this 2 delta cross 2 delta box, no? It should come, right, because your closest pair here is 1. So, it is a 2 cross 2 box, right. So, if there are any points which say like 0.5 apart, they should be within this box, right, and I have not missed any point in the box. I argued there can be at most 12 points in this box, say 5, 6, 12, whatever is the number, and what I did was, standing at a point, I looked at the next 12 points having y coordinates less than it. So, I should not have missed it, right, because see, if there are 2 points whose distance is 0.5, then their y difference should be less than equals to 0.5. So, and what is the size of this box? 2 cross 2. So, I must not have missed it. Agreed?
on that first box and the next 12 points on the second box. But how do you ensure that the last point of the first box and the first point of the last box, they are not like less than delta alpha?
So, I will also compute there, right. I am not missing anything. That is the issue. This box is being hanged at each and every point within this zone. There are order n many such points in this zone, right. So, there will be hangings for each and every one of them, and for each such hanging I look at the next 12 points, because I know that my closest pair can only come for this point from its next 12 points, from the next one next 12 points. So, then it is not missed, right. See, what you have to appreciate is points in this zone have an order on their y coordinates. So, if there are 2 points which are close by here, they are not going to be missed in any way, right. What you are trying to say is, if they are coming closest pair here and maybe there, but then again there will be a hanging for this one, no. So, what you are trying to say is here and possibly here, right. Sorry, I mean, let me say here and on the right, but then again there will be hanging of a box here, right, no. Right, that is what I am saying. So, I am hanging the box at each and every point in this zone, and for each such hanging I am looking at the next 12 points. I compute all pair distances, but it is order n, right. Okay.
For the next 12 points, so we have pre-computed the
Sorted on the y coordinates,
y coordinate, but we don't care about the x coordinate.
but the x coordinates I know are within this zone, right. That is what I said.
What's the pre-computed
Sorting is n log n. Sorting for all the points based on their y coordinates, that is a pre-computation before your recurrence, right. Now, you have computed this delta L, delta R, you have figured out this zone, right. Now, what you do is you march on your sorted y list. I figure out what is the time taken, order n, right. I pick up each point from this list and check its x coordinate if it is lying within this zone, order n, right. So, we did this in this, right. So, this is order n log n for this recurrence thing, and there is obviously an order n log n for sorting. So, total n log n. Okay. So, before I wrap up this, let us look at kind of the dual problem of this one, which is like someone wanted to solve this problem to solve the closest pair problem, right. So, let us do this problem. So, I have a set of points P, n points again, each P I is in R2. Oritra, it finishes at 10:30, right? Okay. So, it is in R2, and as in the earlier case, my goal is find the pair of points that is farthest apart. So, the problem is clear, right? Okay. So, you have points and I want to figure out the farthest point. Again, the trivial algorithm is look at all possible pairs NC2 order n square many pairs, compute the distances, take the maximum. So, n square is trivial. How do I do in n log n, right? Like we solve the closest pair in n log n. So, let us see if we can do farthest pair in n log n. Now, making a divide and conquer work here is going to be problematic, right, because now your farthest pair would come from far off distances. So, there is in this problem a kind of a notion of extremity, right. Okay. Now, let us figure out what that extremity is. Now, if I can say for example, define a polygon on this set of point that tightly fits, yes, I heard the name, it is the good, and that is what we will study next. Okay. So, given this set of points, if I can figure out the convex hull of the set of points, then obviously you understand that, say for example, these 2 points cannot be a competitor for the farthest pair. The competitors have to come from the convex hull only. Now, say again, I mean, say for example, we will study very shortly that this convex hull can be solved in n log n time, but then again it might so happen that n many points are on the convex hull itself, right, or even a constant fraction of this n points are on the convex hull, then if you are going to look at all pairs of this convex hull, then again we are back into the same domain, right. So, we will come back to this problem in the tutorial session in towards the end of the day, but look at one thing. So, if I take a point and draw this distances, can I say anything about these distances? It is not very easy to say something about these distances. You might falsely think that they would be nicely unimodular, that first the distances would be small, they keep on increasing and then it is not that case, it is not that simple. Okay? The distances really do not follow this pattern for any convex shape, but there is an idea that if you look at say a line through one of these convex hull edges and look at the distance of each point on this line, they do follow such a pattern, right. So, you can exploit this property to solve this furthest pair in n log n, but that we will see in the tutorial. But our next goal is to do convex hull is n log n time. So, we wrap this one off by saying, by looking at the definition of the convex hull problem. So, our input would be again a set of points P, each point is in R2 and my goal is compute convex hull of P. So, what is the definition? So, the definition of convex hull is it is the smallest convex set that contains P. So, look at all convex sets that contain P, take their intersection, you have the convex hull, right, and one can show that this would be the the minimum perimeter polygon that encloses